Hello everybody, today is day 2 on probability and we're turning and looking in chapter 10 in the MHH. Grab my pen out here, so MHH section of the book, the second half, 10.2, 10.3, and 10.5. This is going to be on counting principles. Okay. Alright, so we have some theoretical probability here. Okay, so if the sample space, we talked about this last time, but the sample space for an experiment is written in the way that all outcomes are equally likely, then the probability of the event E is below number of outcomes in E over the total number of outcomes in the sample space. Okay, so probability and counting. In order to use the definition, we must be able to count two things: the number of outcomes in E, and the number of outcomes in the sample space. Our goal in this section is to develop some counting techniques used in calculations of these probabilities. One option is to count each step by listing outcomes. We did do this in the last section. For example, let's take a look at a coin. It's tossed 4 times in succession, and we want the probability of getting exactly 3 heads. So we can actually list this all out. I'm going to use H for heads, T for tails, and here are all my sequences I can get. Okay, from our extremes, all heads to all tails, and then everything in between. And notice here, this is where we have 3 heads, 1 tail. This is all where we have both 2 heads and 2 tails. Here's where we have 1 head and 3 tails. Okay. So the probability of rolling exactly 3 heads, we're looking at this column right here, and there's 4 of them out of a total of 16. So the probability is a fourth. As another example, suppose we toss a pair of dice and we want the probability of getting an 8. Again, we can list all the outcomes, which I'll show you on the next screen here. And there's a total of 36 of them. And which ones have exactly the sum of 8 is 5. So here's the combinations that we get. Again, notice how this is starting to get more and more lengthy as we kind of add different components to it. So now we're tossing 2 dice instead of just flipping 1 coin, that type of thing. But again, you can see sum of 5. We'll go back here. I'm sorry. The sum of 8, there's 5 chances of that out of a total of 36. Okay. All right. So the coin example, we have 2 choices, right? So either heads or tails and 4 tosses. So in other words, 2 choices each time. And there's 4 of them. So that's why we multiply 2 times 2 times 2 times 2 to the 4th, right? Because we did it 4 times. For the dice example, there were 6 possibilities for each die, so there were a total of 6 times 6, or another is 6 squared. That kind of gives us a little bit of a general rule here, which is called the fundamental principle of counting. Suppose we have a task that can be broken down into a sequence of k steps. So further suppose that we have n1 ways to do step 1 and 2 ways of doing step 2, etc. Okay, so in other words, the total amount of ways we can do that is taking n1 times n2 times n3, until we reach the end there, multiplying them all together. Super important. The fundamental counting principle can be used only when counting in ordered arrangement. So ordered arrangement. The statement explicitly states that the task is broken down into a sequence of steps. Okay, so let's look at an example here with a fundamental principle of counting. A license plate consists of 3 letters followed by 3 digits. How many license plates are possible, first of all, and how many license plates are there in which no character is repeated? Okay, so again, we're going to figure out the possibilities first with the license plates here. So what are the possibilities? Well, again, we have 3 letters, so we have 3 slots for the letters in the first spot, and then we have, so this is the letters, and then we have 3 spots for numbers after that, so there's a total of 6 slots. Well, let's think about this. When we do a license plate, we have the options of A through Z. So I'm just literally kind of writing down, here are my options for each of these scenarios. I could have A, I could have A, B, C. Doesn't matter if they repeat or don't repeat. I have 26 letters for each slot of the first 3 where the letters go. Same thing for when I'm talking about the numbers for the second part, all right? Because this was letters here. My number options are 0 through 9. And that makes 10 numbers. And again, it doesn't matter if they repeat. If I do 2, 2, 2, if I do 2, 5, 7, it doesn't matter if they repeat or not. It's what are my options I have. So I want to multiply all those options together. 26 to the third times 10 to the third. And that'll give me my total possibilities. Okay, and that's a rather large number. I didn't go ahead and multiply that out. You're welcome to do so. But again, I just left it as 26 to the third times 10 to the third. The second part of the question. Okay, so now we want it without repeats. So no repeats. So again, let's think about this. I still have all my letters for the first slot. So I have A through Z. So that gives me 26 right here. But I have to take one away. I don't know what letter it is. I don't know if it's A. I don't know if it's Z. I don't know if it's M. But I'm taking one away. So if I take one away, and I chose the easy one of A, that means I have 26 letters left. And again, if I take another one, 25 letters left. If I take another one away for the third slot, again, I'm going to make it easy. I'm going to say I chose B. I have 24 to choose from. So now I'm multiplying 26 times 25 times 24. And it works the same for the numbers. So I initially have all my numbers, 0 through 9. And now I take one away, and then I take another one away. So now I multiply those all together, and that gives me a total possibility of 11,232,000. Okay, so again, this is forming a license plate without repeats. And you're going to see me do this method a lot, where I say, okay, here's how many slots I have, what are my options for each of them, and I fill in the blanks of how many total options I have for each blank. Okay, a few more examples. Let's just first, we'll read the examples and we'll take one at a time. How many social security numbers are possible? Okay. B, what is the probability that a social security number has no repeated digits? C, what is the probability that a social security number has at least one repeated digit? So let's first tackle the first one. How many possibilities are there? Okay. Well, you have the social security numbers of 3 slots, 2 slots, and then 4 slots. There are 10 choices for each slot. So again, I have 0 through 9 options for every single one of them. So again, there are 10 choices for each slot. So I would be doing 10 times 10 times 10, which is 10 to the 9th. Okay, so again, I didn't multiply that out, but that would be our total numbers of social security numbers available. Okay. Well, part B said, was it probably that a social security number has no repeats? So again, if we think about how we did this one, for the repeats, right? We now, again, we still have the same amount of slots here, but each time it's decreasing by 1 because we can't repeat any numbers. So we would do 10 times 9 times 8 all the way up and fill all of our 9 slots and then multiply all those numbers together. Okay, so that is your possible repeats, right? Okay, so without repeated digits. So the probability, so remember our probability is between 0 and 1 or 0 and 100% if you're thinking about percents. So we're not just finding the total possibility of social security numbers with no numbers repeated. We want the probability of no repeats. So the probability of no repeats would be how many no repeats are there over the total amount possible. So 3,628,800 over 10 to the 9th, which gives us a 0.0036 probability. Okay, so really kind of important. Let me go back to this real quick. How many versus what is the probability? Realize the difference between those questions. This is typically going to be some sort of large number A probability, again, is between 0 and 1 is a decimal, or 0 and 100%. So you're finding the total possibilities over the total number. I should write this as total number. There we go. Okay, so this third part is a probability again. So what's the probability that a social security number has at least one repeated digit? So we have to figure out how many possibilities there are for at least one repeated digit divided by the total number, which is what we had in A. So this is part A, this is part B, part C. So again, noting that no repeats and at least one repeat are opposites of what we just found, right? So what we just found here is the opposite of at least one repeat. So instead of doing a ton of work going through this process of figuring out our 9 slots and which one goes in which, we literally can take 1 minus the probability of no repeats, and that gives us our probability. Okay, and you're going to find that we use this opposite idea frequently. Okay, so sometimes it's a lot easier to find the opposite of it and then do 1 minus, because all your probabilities, the opposite of your probability should add up to, again, 1 or 100%. Okay, so a little bit of review here in terms of some math and terms, and in this case is a factorial. Yes, it's an exclamation point, but we read it as a factorial. So in factorial, this is the notation for that. Okay, so again, we're working with positive integers, means you count down. So if I had 5 factorial here, okay, and I'll put another example on the other page. I start with the number 5, and I count all the way down until I get to the last number, and I multiply all those together. Okay, so 5 times 4 is 20, times 3 times 2, so that would give me 120. It is also important to know that 0 factorial is equal to 1 factorial, which is also equal to 1. All of these are equal to 1. Okay, so here's a couple more examples written out with a variable in factorial. So again, you just keep subtracting until you get to 1. Okay, but it's a lot easier when we think about it in terms of numbers. So if we do 7 factorial, I can either list it all the way out until I get down to 1, or I could write it as simply 7 times 6 factorial, because 6 factorial is equivalent to 6 times 5 times 4 times 3 times 2 times 1. So we can kind of stop it wherever we want. Like in this case here, we did 7 factorial, 7 times 6 times 5, and then we did times 4 factorial. Again, that represents 4 times 3 times 2 times 1. So it's also, again, equivalent to the original of 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay? All right, so we're going to be using that slightly as we go through some more probability. But let's do a few of these here. Okay? So 4 factorial. Again, hopefully you realize that is literally, again, just 4 times 3 times 2 times 1. Okay? Now this one, 4 minus 1 factorial, this is in parentheses, so we actually want to do that first. So this is equivalent to 3 factorial. Parentheses always come first. Now you come down here and see that's equal to 3 times 2 times 1. Okay? Couple different ways to do C. If I write it all out, this is what I would have. And hopefully you'll see here, 1's cancel, 2's cancels, 3's cancel. So it's really just 5 times 4, which is 20. So the other way of doing it is realizing that 3 factorial is within 5 factorial. So you can just literally cancel those out instead of having to write all of those terms and do 5 times 4 and get that to be 20. Again, either way would really be fine. It's just the higher these numbers are, this notation down here is just definitely a little bit easier and more of a shortcut because you don't have to, again, write all those terms out. Okay. All right. So another example here. How many ways can 8 people line up for a photograph? Okay, so we have 8 slots to fill in because we have 8 people. 8 choices for the first one. Then again, we've taken someone, we've lined them up. So then we have 7 for the second slot. Then we have 6, 5, and we're going to just keep going all the way down. So if you notice, that is equivalent to 8 factorial. Okay. So ordered arrangements. This is order. There is order here. Okay. The order does matter in this case if you're standing next to your uncle versus standing next to your aunt, that type of thing. Okay. So there are k factorial ways to order k distinct objects. The number of ordered arrangements of k objects chosen without replacement from a collection is represented by n factorial over n minus k factorial. And the number of ordered arrangements of k objects chosen with replacement, so this one is without replacement, this one is with replacement, is n to the k. Okay. These formulas are recorded mostly for future reference. Okay. When actually counting ordered arrangements, it's usually easier to just use the fundamental principle directly. Write out the correct number of slots, like we were talking about the license plate. We did the slots like this. And then fill in the number choices for each of them. Okay, so when we do these next examples, I'm going to follow this method right here. Okay. How many ways can you line up 6 different books on a shelf? And I do want to point out, all of these examples talk about order. Okay. How many ways can you line up 6 different books on a shelf? Well, I have 6 slots. I have 6 books for the first slot. 1 book's chosen, so then I have only 5 for the next. Another book is chosen, so I only have 4. And you can hopefully see the pattern from there. And then multiply all those together. And that should be, again, go ahead and just use your calculator for this. 720. Okay. Next one. How many 4-letter words can be made up of from the American alphabet, which I'm always going to assume that, 26 letters. I will not change that on you if no letter can be repeated. Okay, so again, 4, 1, 2, 3, 4. No repeats. So that means I have 26 here. If I choose one here, I can't repeat it over here, so I have to decrease it by 1. Decrease again, and decrease one more time. And again, I multiply those all together. That's the fundamental counting principle. So again, using your calculator, fairly large number there. So it should be, make sure I got all my, 358,800. Okay. All right, I'd like you to pause the video on this one. Try that third one on your own. Again, fill in the slots and see how you do with this one. Okay, so this one, you could repeat the letters. That's what was different from the middle one. So each slot had 26. So obviously you have more choices, 456,976. Okay. These, again, all represent order. Okay. And we're thinking about what we call permutations. Permutations mean order. Okay, and that's what I'm referring to on this slide here. Ordered arrangements of k objects chosen from n objects is written as npk, right? So n and k are kind of the subscripts there. So npk is equivalent to n factorial over n minus k factorial. Again, to actually calculate the number of permutations, we generally just use the fundamental counting principle. Actually, it should be fundamental counting principle, FCP, a little typo there. The TI-84 will also calculate the number of permutations for us. If you go to Math, PRB, so that stands for probability, and then select NPR, you will literally see that in your calculator. And I'm going to pull up my calculator here in just a moment so I can show you this. So to calculate 10P4, we would enter in 10 NP4 and NPR4 followed by enter. Okay, and we should get this. So I'm going to go ahead and get my calculator. If you don't have now this is a graphing calculator, TI-84. If you don't have one, you're definitely going to have to do the slots, but I would suggest getting one and using one so you can use it while you're doing these. You'll need it for permutations and combinations. So pause the video if you don't have yours and then grab your calculator. Okay, so again, oops, sorry about that. We're going to plug this in, 10P4. Some operating systems are a little bit different, but I'm going to go ahead and plug in the 10 first. And then you'll see I'm going to go over here to math. And then I got to highlight, in my case, it says PROB, probability, instead of PRB. And then you'll see we have NPR here, we have NCR. And I also want to point out we have factorial in here as well. So just to point that out, but I'm going to go to number 2. Those are the 3 that we're going to use. Enter, and then I would hit 4. So you can notice it shows up just like I'm looking at it right over here, 10P4, and then I push enter, 5040. Okay. All right, so now we're going to talk about combinations here. Okay, so if I go to combinations, the difference here is it's not ordered. Okay. So arrangement of K objects chosen without replacement from a collection of N objects are called combinations. So this is NCK, right? So it's N factorial over K factorial times N minus K factorial. Okay, so just like with permutations, you can actually use your calculator to help you find this. And I'll switch over to my calculator here in a moment. Same idea, hopefully. So again, if you remember though, mine did say PROB here. Again, there can be some different operating systems for 84s depending upon the version you have. But the difference is now when I do 10C4, I'm going to do the C, the combinations instead of the permutations. Okay, so go ahead again, grab your calculator if you don't have it, and then let's plug this in. Okay, so I'm going to plug this in. So again, I'm going to do 10. Then I'm going to go up here to math. And you'll see that I again have to highlight PROB, probability, go to NCR, which is number 3, enter 4, and enter. So that gives me 110. Okay. So that's the difference in how you find those in your calculator. Okay. Let's go ahead and go back to our notes here. All right, so a couple different items here. These numbers are often called binomial coefficients because they appear in the binomial theorem. NCK counts the number of subsets of size k chosen from an n element set. Okay, so again, a little more facts here. These are equivalent to each other. So in other words, it might be a little bit easier for you to look at the actual example there. Sorry, the actual example there, which is 12C5 is equal to 12C7. You'll get the exact same answer. So here's again an example. Suppose that we have 12 friends and we want to pick 7 to attend a dinner party. That's the same thing. Choosing 7 to attend is the same thing as choosing 5 not to attend. Okay, so again, those would be equivalent to each other. So important little fact there. So an example where no order matters. So a committee of 4 is to be selected from a class of 7 men and 9 women. So again, no order. And why is this so? I am on the committee whether I'm chosen first or if I'm chosen last. That's why order doesn't matter here. Okay? So A, and how many ways can the committee be selected? So in this case, because there's no order, we do 16C4. Okay? Hopefully that does make sense. No order. Part B, how many ways can a committee be chosen to have exactly 3 women? Okay, so again, difference. Let's look at it, go back to A here. So this is how many ways can the committee be selected? So we actually have 16 because a total of 16 people are on the are in our pool that we can choose from, and we're choosing 4 of them. So that's why we chose 16C4 in this case. And again, the order didn't matter. Now we're being more specific. How many ways can the committee be chosen from exactly and have exactly 3 women? Well, now we're saying, okay, there's 9 women. So we have to do 9C, and we want exactly 3 of them. But we still have a 4-person committee. We're missing 1 slot if we only have 3. So 7 men fill the, we have an option for 7 men, and we have 1 of them that fills that slot. And by fundamental counting principle, we multiply those together, which is exactly what they're doing right there. So there's 588 committees with 3 women. Okay. All right, another example. What is the probability? Now this switches. 0 to 1 would be our decimal answer here, that the committee has 3 women. Well, that's what we just did in Part B. This was Part B here, and this is Part A. So we did Part B divided by Part A, because the number of committees with 3 women is 588 over the total number of committees, which is 1,820. So that gives us a probability of 0.323. Okay. Next question. What is the probability that the committee has at least 3 women? Okay, so let's take a look at this. If the committee has at least 3 women, it has either exactly 3 or exactly 4 women. So then we need to figure out the probability of having 3 women and add it to the probability of having 4 women. Okay, so from our previous example, we already know the probability of 3 women, which was 0.323. So we need to now focus on, okay, what's the probability of having 4 women? So we need to figure that, calculate that. So having 4 women, so remember, it's a committee of 4, and we have an option of 9 women. So this, when we choose 4 women, it's filling all of our slots of our committee here. So to find the probability of only having 4 women, that would literally be 9C4. Okay, so there'd be 126 ways for this to happen. And again, if you remember from Part A, there's a total of 1,820 committees. So we do the probability of picking 4 women divided by that. So that gives us this probability here for women. Again, we already calculated this from Part C, which was, and I apologize, this really should be switched around to match this. The probability of 3 women is 0.323, where the probability, and let me use a different color here, of having 4 women is 0.0692. Add those together, that gives us the total probability of 0.3922. So a little over 39%. Okay. Next example, still the committee problem. Was a probability that the committee has at least 1 man. Now hopefully you realize this is the opposite of having all women. So if we do 1 minus the probability of having all women, which we just did, we just calculated, so that would be the probability of having 4 women. Exact same thing, which we just calculated again on the previous slide to be 0.0692. And we subtract that from 1. Gives us the probability of 0.9308. So 93% where it's at least 1 man is on the committee. All right, so a couple more odds and ends here before we do a few more examples. Usually we are using more than one counting principle at a time. And the overall strategy for computing probabilities is as important as the formula is used. Okay, so we have the fundamental counting principle, permutations, which is order, and combinations, which is not ordered. Okay, So we're going to do a few of these examples here on this next page. In how many ways can we choose a president, vice president, and treasurer? So the first thing I want you to think about is, this is not a probability problem. It just says in how many ways. So it's a permutation or a combination. Does order matter? And it does. This is like having first, second, and third. If I get first over second, there's a difference there. So president over vice president, order matters here with this one. So order does matter. So this is a permutation. So I have 11 women and 9 men. Doesn't specify any difference between men and women here. So in this case, it would be 20, because this would be 20 total here, right? If I added those together. P, and I'm choosing 1, 2, a president, a vice president, and a treasurer. So a total of 3. Okay. So that is also the same as doing slot 1, slot 2, slot 3. I have 20 options for the first slot. I chose somebody. So now I have 19 options for the vice president. I chose somebody. Now I have 18 options for that treasurer. So realize these are exactly the same thing there. Whether I do 20 times 19 times 18 or 20p3, that should give me 6,840. I'm not going to plug these in my calculator. If you are having calculator problems with that, please just let me know. But again, that's just either arithmetic here, or am I doing the permutations under your math probability functions in your calculator. All right, so let's take a look at B. If we chose a president, vice president, and treasurer, now we're talking about what's the probability that the president and vice president are both women. Here we have a little more work to do. Okay, so we're still doing the total here, right? So our total is going to be, let me put this on the bottom, out of 6,840. Okay, but now we need to figure out president and vice president if they're both women. Well, I have 11 women, and I'm choosing 2 spots. So 11p2, because order still matters. But I still have that 1 slot left over of the treasurer. So now I have 9 men, so times 9, and I have 1 slot left over. So I'm going to do 11p2 times 9p1 over 6,840. Okay, so if I multiply those together, so if I first calculate this, I got that to be 110 for 11p2 times, and then 9p1, I got that to be 9 over 6,840. So then when I calculated that, I got that to be 0.1447. Okay, now I have a lot of writing on here. I'm going to actually erase this, and then I'm going to put just the answers up here, so I can have a little more space to do C and D here. So I'm going to erase all of that. The answer to A, which 6,840. The answer to B was 0.14, and that decimal keeps going away, 1447. Okay, so let's talk about C here. Choose a different color. How many ways, so again, not probability, how many ways can we select 3 individuals to attend a conference? Different than A. No order. Again, doesn't matter if I'm chosen first or if I'm chosen last, I still get to go to the conference. So again, I still have a total of 20 people. So I'm going to do 20C3. And again, plugging that in my calculator, 1,140. Now, switching colors again. Probability. We're talking between 0 and 1. It's probably that all 3 individuals chosen to the conference are women. So this 1,140 is our total amount of ways we can choose 3 individuals to go to the conference. Well, now we're talking about women. So again, I have 11 women, and I'm choosing 3 of them. That takes up all 3 slots. So I only have to do that one calculation. So if I plug that in my calculator, I got that to be 165 over 1,140, which gives me that's a decimal point there. Sorry, that does not show up very well, but 0.1447 again. Okay? It just happens to be coincidence that they're the same there. All right, so now let's kind of talk about this inclusion-exclusion probability. Okay, so this is when we're talking about, for example, when we were doing the committees. What's the probability that a committee has at least 1 man? Well, that was the opposite of having all women. So we did 1 minus the probability of having all women. Same sort of idea here. Okay, so when we write NA for a number of outcomes in an event, and for any events, so NA plus NB minus N, the combination of the both of them, right? If A and B are disjoint, so they don't overlap, we literally just do, if we're choosing A or B, it'd be NA plus NB. We don't have to do anything if there's overlapping. So an easy way to think about this is as follows, because I know that can be a little complicated looking at the symbols. If we add up the number of outcomes in A and B, then any outcome that is in both sets gets counted twice. Therefore, we subtract, so we don't duplicate. That is what this is saying right here. Okay? So let's think of an example here. We have a survey. It says, in a poll, 2,000 U.S. adults were selected at random and asked to agree or disagree with the following statement. Job opportunities for women are not equal to those for men. Here are the results. The results showed that 1,190 people agreed with the statement, 700 women agreed with the statement. If half the people surveyed were women, how many men agreed with the statement? And B, how many men disagree with the statement? Well, if we think about doing a Venn diagram, we should easily be able to figure these out by knowing there was a total of 2,000 adults. Half the people surveyed were women, and also knowing 1,190 people agreed with the statement and 700 women agreed with the statement. So let's kind of draw a Venn diagram. And for those of you who don't know what a Venn diagram, usually you start off with a rectangle, and you do a couple circles here. We're going to have a circle of women, and then we're going to have a circle, we're going to do agree. People that agree. Okay? So here's what that's going to look like. So define sets and draw a Venn diagram. So again, we have, this is the whole subset here. All right? The rectangle, that's our whole subset. Women agreed. This is where they overlap. So this would be the women that agree in the region 2. Okay? So hopefully that makes a little bit of sense there. So here's our facts again, just repeating those facts. So we are given 2,000 people surveyed, all right? Half the people were women, so that means 1,000 of them. Oops. The number of people who agreed with the statement is 1,190, and 700 women agreed with that statement. So like they're saying up here, determine for each region in the Venn diagram starting with the innermost region and working out. Well, the innermost region would be region 2, which would be women that agree. So that's what we filled in. So we had 700 women agreed. We knew that there were 1,000 women total surveyed, so then that brings us to 300 didn't agree. We also knew that 1,190 people total agreed, so if I subtract these two, I get that to be 490 agreed. And then what's left over is outside of both of those ovals and the intersecting portion of 510. Okay, so then that should be able to really tell us more information, and we can depict that by men who agree with the statement are those members of the set of people who agree and who are not women, which is region 3. Okay, means that 490 men surveyed agreed that the job opportunities are not equal. The men who disagreed with the statement can be found outside the circles of people who agree and people who are women. That corresponds to region 4. There must be 510 of them. 510 men surveyed disagreed with job opportunities are unequal. Okay, so this concludes our second day of probability, focusing on counting principles.